Hello everyone. In this video, I will be discussing about calculation of wavelength maximum for alpha, beta unsaturated compounds. It may be carbonyl compounds, may be aldehydes, ketones, esters, etc. So we have seen the presence of ethylenic double bonds, that is symbol dienes, causes high intensity of pi to pi star transitions. Pi to pi star transitions. That band will be coming near 170 nanometer, that we have already seen. That is simple C double bond C type of transition. On the other hand, an isolated carbonyl group like C double bond O exhibits a high intensity pi to pi star transition near 190 nanometer. 190 nanometer. And also there will be a low intensity symmetry forbidden pi to pi star band around 290 nanometer. So in this both transition, this will be high intensity transition and this will be low intensity transition. However, when a carbonyl group is conjugated with an ethylenic double bond, so what does it mean? Means this carbonyl compound, if you are considering this one, an aldehyde, and this one, this is an aldehyde, right? Both are aldehydes. So which one is conjugated? If you are looking into this structure, the conjugation means this should be in a conjugation. The double bond will be shifted over here. There should be a complete delocalization which is absent over here. But if you are seeing at this structure, this could be shifted to here and this could be shifted over here. So that means this is having a conjugation like here positive charge, double bond, O minus. So this is what is meant by conjugation. So if a double bond is conjugated with carbonyl compound, the conjugation brings about bathochromic shifts to both the bands. In fact, alpha beta unsaturated carbonyl compounds are characterized by a high intensity pi to pi star transition, and this alpha beta unsaturated one normally will have that that carbonyl compounds will have high intensity transition between 215 to 260 nanometer region, and this is a high intensity one, and a low intensity transition pi to pi star at a range of 310 to 330 nanometer region. This is a characteristic of alpha beta unsaturated compounds, alpha beta unsaturated compounds, because the carbon compound is in conjugation with the double bond. So there are some just as in the case of dienes and polyenes, there are some empirical rules which are called Woodward-Fieser rules or Woodward-Fieser-Scott rules that can be used to predict lambda max. That means lambda max means absorption maximum for calculating this pi to pi star transition. So the basic values for different functional groups. In the case of ketones, acyclic compounds, that means this type of compounds are not cyclic. Okay, so acyclic or six-membered ring system, both will be having an basic value of 215 nanometer. Basic value 215 nanometer. If you have, so acyclic means this type, and six-membered means like this. Six-membered with the unsaturation in conjugation. Okay. Now 5-membered alpha beta unsaturated ketone means like this. So it is having a lesser lambda max compared to 6-membered. It is 202 nanometer. Now if it is an alpha beta unsaturated aldehyde like alpha beta unsaturated aldehyde like this one, that lambda max value will be 207 nanometer. You have to remember this, 207 nanometer. And in the case of alpha beta unsaturated acids like this, carboxylic acids, or it could be that H could be ester, then that value, basic value will be 197 nanometer. 197 nanometer. So this is very important to remember. So alpha beta unsaturated ketones which are acyclic or 6-membered will have the value of 215 nanometer, whereas for 5-membered ring system like this one, it is 202 nanometer, and for aldehydes it is acyclic compounds, it is 210 or 207 whatever maybe, and if it is a 6-membered ring system it is 250 nanometer, if it is a 5-membered ring system it is 202, and for aldehydes and carboxylic acids and esters it is to 197 nanometer. Okay, so these are the fundamental things that you have to remember about um, the basic value of lambda max for aldehydes and ketones. Now the other things like the contribution that we have seen it for dienes and polyenes, that same thing, that is exocyclic double bond thing, or double bond extending conjugation, ring residues, everything is also present over here also. Additional contribution by these factors are also present over here. So let me summarize what are those things. So we have seen in the case of polyenes and dienes, the contribution of double bond extending conjugation. Double bond extending conjugation, we already see double bond extending conjugation, and the value was, you have to add 30 nanometer into it. Then if you have exocyclic double bonds, then as in the previous cases you have to add 5 nanometer. Now if you have a homoannular diene component, then you have to add homoannular diene component, then you have to add 39 nanometer with the lambda max. So homoannular diene component means, if I am writing an example, it would be like a compound of this sort. Suppose this is an alpha beta unsaturated diene component. Okay, and now if you have another ring system like this and one more ring system like this. Okay, now this extending conjugation over here like this. Okay, now if you are seeing over here, this is our basic thing. Okay, so basic value for this alpha beta unsaturated, which is 6-membered, that value you have to take 6-membered one, the value is 215. So 215 nanometer plus. Now if you are seeing over here, this diene is present within the same ring. Two double bonds are on the same ring. So here you have to add 39 into it. Other things are also there along with this 39 nanometer. Now let us see. So this is about the additional contribution. Now some more things are there depending upon the substituent present. So let me show you what are those things. Suppose you have systems attached at positions alpha, beta, gamma, delta. Okay, so if you have alpha substituent, so I will show you what is meant by alpha substituent, beta substituent, and gamma substituent by drawing a suitable example. Okay, suppose you have a ring system like this. This is double bond over here, ketone, alpha beta unsaturated ketone, right? Then one more ring is present in this, suppose like this, and here one CH3 group. Okay, like this. So if you are seeing this, this is our alpha beta unsaturated ketone, right? This is our alpha beta unsaturated ketone. Base value will be for 5-membered ring, which is a 5-membered ring, right? So that will be 2NO2, right? So 2NO2 plus. Then with respect to this one, this is the alpha carbon, this is the beta carbon. Okay, now this is gamma carbon, delta carbon, right? Here also this is gamma carbon, delta carbon, like that. It will go on like that. Now, if you have alkyl substituent or at the alpha position, if you have alkyl substituent, you have to add 10 nanometer. Now, if you have ring residue or alkyl substituent at beta position, so this is the beta position, then you have to add 12 nanometer. And if you have alkyl substituent or ring residue at gamma position, you have to add 80 nanometer, like that. So while doing some examples, we will greatly understand about those things. Now similarly, if you have instead of CH3, if you have alkoxy group means if you have instead of CH3, if you have OCH3, so this is methoxy group. Then at alpha position, if you are having OCH3, then you have to add 39 nanometer. Beta substituent means 30, then gamma 70. Now instead of OCH3 group, if you have OH group, that means hydroxyl group. So if you have OH substituent at alpha position, then 35 nanometer. If it is at beta, then 30. If it is at gamma, 30. Then so on. Now, if you have halogen, that is chlorine substituent at the alpha position, then you have to add 15 nanometer. If chlorine has beta position, then 12. At gamma position, 12, and so on. Now, instead of chlorine, if you have bromine substituent at the alpha position, you have to add 25 nanometer. Then if it is at the beta position, then 30 nanometer, and so on. So these are the factors or contribution that you have to add with the basic value of different alpha beta unsaturated carbonyl compounds depending upon the position of the. Now another thing is that if alpha beta unsaturation is present on both sides of the carbonyl group, then the value of maximum absorption is calculated by considering the most highly substituted conjugated system. Suppose you have a ring like this. Okay, so here also double bond. Now here extending conjugation, here double bond, some like that. Now if you are seeing over here, there is no substituent. So there is two possibility of calculating lambda maximum. either through this side, like, because here alpha beta unsaturation, or through this side. So which case we will consider? So if you are considering this side, there is no alpha substitution, only beta substitutes, 2 beta ring residues. Okay. So the value will be 202 plus 2 into 2 ring residues at the beta carbon. So 2 into 12, 24. So you will be getting 6 to 226 nanometer. Now if you are going in the other side, so the basic value will be 202 plus, so this is the alpha carbon, this is the beta carbon, and alpha carbon there is nothing, and beta carbon you have ring residue. So ring residue at beta carbon contributes 12. Now see here extending conjugation, or you can add what the basic value uh, basic value for the homoannular, contribution by the homoannular diene component, right? So homoannular diene component 39 nanometer you have to add. Then further this double bond, alpha. Now you can consider here also alpha, beta, gamma, like that. Okay, beta position you have ring residue. So this is the contribution it is having. So for 13, 1 plus 3, 4 plus 5, 253. So this will be giving highest value because the highly substituted side will be giving greater value. So this type you have to count. That is this another rule. So what does it mean? If alpha beta unsaturation is present on both sides of the carbonyl compounds, you have to take that value of maximum absorption by considering most highly substituted conjugated system. So that is happening over here. Now we will discuss about solvent correction in calculating lambda maximum. Okay, so in polar solvents, that is solvent more polar than ethanol. Suppose ethanol, say water as solvent. The pi to pi star, the observed pi to pi star band was shifted to longer wavelengths, longer lambda max as compared to those observed in ethanol. So in ethanol it will be at a particular wavelength. If you are recording the same compound, if you are recording the UV visible spectra of same compound in water which is more polar than ethanol, this pi to pi star was found to be, that band was found to be at a longer wavelength. Okay, now in a less polar solvent, if you are recording it in a less polar solvent, say this is more polar solvent. Now if you are taking chloroform or diethyl ether or hexane, that type of solvent, if you are recording, the same band was shifted to shorter wavelength. So polarity has an influence on the shift. Okay, so in more polar solvents, it will be shifting into higher lambda max, and if you are taking low polar solvent than ethanol, it will be shifted to shorter wavelength. So therefore, in order to get lambda max value for the pi to pi star band in any solvent other than ethanol, there should be some correction factor which should be added or subtracted depending upon the polarity of the solvent. So this is the case where I was discussing. Okay, in ethanol is keeping as the standard for this one, and here if you are seeing this water is more polar than ethanol, so you have to add 8 nanometer into it. So methanol is as good as ethanol, so there is no correction, it is 0 nanometer. Now if you are seeing these are less polar compared to ethanol. So this is water is more polar compared to ethanol. So here you have to subtract. So if you are recording in chloroform, you have to minus 1 nanometer. If you are recording in dioxane solvent, solvents name is dioxane. minus 5 nanometer. If it is diethyl ether, then minus 7 nanometer. So if it is normal hexane, you have to subtract minus 11 nanometer. If it is cyclohexane, again minus 11 nanometer. So you have to add the solvent correction also to the calculated lambda max by describing the pi to pi star transitions of alpha beta unsaturated compounds. Now let us go to some solved problems for calculating the lambda max which is recorded in ethanol. So in the first example, if you are seeing, first you have to identify this is an acyclic alpha beta unsaturated ketone. So this is our ketone moiety and this is the alpha carbon, this is the beta carbon. So this is an acyclic enone. So the basic value for acyclic enone, okay, double bond ketone for ketone ONE, so enone. So that base value that we have already seen, it is 215 nanometer according to Woodward-Fieser rule. Now there is one alkyl substance at the alpha carbon, so you have to write alpha CH3. So that means if it is at the alpha position, you have to add 10 nanometer. Now if you are seeing at the beta carbon, there are two beta substituents, so you have to write beta CH3. There are two and the contribution for each is 12 since it is in the beta, so it will be 24 nanometer. And the total will be total lambda max, and it is in ethanol you have to specify solvent over here. The total you will be getting by adding this, so it will be 249 nanometer for this acyclic enone. Now let us move into the second compound. So this is a cyclic 5-membered ring system. Okay, so the basic value for this 5-membered system, basic value for the 5-membered enone will be equal to 202 nanometer. Now this is the alpha carbon, this is the beta carbon. Okay, alpha carbon there is no alpha substituents. Now in the beta carbon, here one ring residue, here one ring residue. So you have to write beta ring residue. Beta ring residue is 2. So 2 into 12 is equal to 24 nanometer. Now if you are seeing this double bond, this particular double bond which is exocyclic to the second ring. So there is only one such ring. Okay, so one exocyclic double bond, its conjugation is 5 nanometer. So you have to write 5 nanometer. So the lambda max total in ethanol solvent is calculated to be, if you are adding, you will be getting 231 nanometer. Okay, now let us move into the third compound. Okay, this one. So this is a 6-membered alpha beta unsaturated ketone. So the basic value, or you can consider this as a acyclic one also, because this ketone is the outside. Okay, for both the things the base value will be equal to 250 nanometer. Now you know this is alpha carbon and this is beta carbon. In the alpha carbon there is one ring residue, so you can write alpha ring residue. Contribution is 10 nanometer. Now if you are seeing at the beta, there is one beta ring residue. So beta ring residue. So the contribution is 12 nanometer. So if you are adding, you will be getting 237 nanometer in ethanol solvent. So lambda max in ethanol solvent was found to be this one. Now move into the fourth component. So this is again a 6-membered enol. So the basic value again will be equal to 215 nanometer. 215 nanometer. So here this is the alpha carbon, this is the beta carbon. If you are seeing there is only one alpha substituent. So alpha ring residue 1. So its contribution is 10 nanometer. Now if you are seeing beta carbon is having 2 ring residues. So beta ring residues 2 into 12 is equal to 24 nanometer. Now if you are seeing over here, this double bond is exocyclic to ring 1 and also it is exocyclic to ring 2, right? So you have to consider both. So double bond exocyclic to both the rings. So double bond exocyclic to both the rings. So 2 into 5 equal to 10 nanometer. So altogether if you are adding, you will be getting 259 nanometer. And let us move into another set of examples. So here in the sixth example, if you are seeing, this is again a 6-membered alpha beta unsaturated enol. So the basic value for this enol will be basic value for this 6-membered enol will be equal to 215 nanometer. Then if you are seeing over here, this is the alpha carbon, this is the beta carbon, this is gamma carbon, this is delta carbon and so on. Now if you are seeing beta, there is no alpha substituent over here. If you are seeing at the beta carbon, there is one alpha, ring residue. So beta ring residue 1. So that means 1 into 12, you have to add 12 nanometer. Now, if you are moving over here, there is a double bond extending conjugation. So here, this is extended to this one. This could be in conjugation, right? Like this. So, double bond extended conjugation is present. So, one double bond extending conjugation. Double bond extending conjugation. So 1 into 30, you have to add 30 nanometer. Now this is the delta carbon. At the delta carbon, you have one ring residue, right? So delta ring residue. For that contribution, the value is 18. So 1 into 18, you have to add 18 nanometer. Now look for exocyclic double bond. So if you are looking into here, this double bond is exocyclic to this ring. So there are no such exocyclic double bonds, only one. So exocyclic double bonds 1. So you have to add 5 nanometer. So altogether if you are adding, the value will be 280 nanometer at ethanol solvent. Now move on to second compound. So this is obviously it's a 5-membered enol, cyclic enol. So the basic value will be 5-membered cyclic ketone, the basic value will be 215 nanometer. Now this is the alpha carbon, this is the beta carbon. Alpha bromine substituent. Alpha bromine substituent is present. So if it is bromine, you have to follow the Woodward-Fieser rule. The contribution is 25 nanometer. Now ring residues. At the beta carbon, one ring residue over here, two ring residue. So beta ring residues. Beta ring residues, how many? 2. So 2 into 12, you will be getting 24 nanometers. Now look for exocyclic double bond. So this particular double bond is exocyclic to the second ring. Only one such. So exocyclic double bond 1. So 1 into 5 is equal to 5 nanometer. So if you are adding, the value will be 269 nanometer in ethanol solvent. Lambda max in ethanol. You have to specify the solvent. Moving on to 8th compound. If you are looking into it, it's a 6-membered cyclic ketone alpha beta unsaturated, right? So the basic value for 6 member, one is 215 nanometer. Now there is one alpha OH substituent and its contribution is 35. So 1 into 35. So 35 nanometer. It's a polar group. OH group is a polar group. That's why contribution is more, 35. Okay. Now if you are looking into the beta carbon, this is a beta carbon, one alkyl group and one ring residue. So beta ring residue you can specify like beta ring residues. So it will be 2 into contribution is 12. So 24 nanometer. There are no extended conjugations, there are no exocyclic double bonds, etc. So that much only. And if you are adding, the value was found to be 274 nanometer. Moving on to the another structure. This is again a 6-membered alpha beta unsaturated ketone. So the basic value will be equal to 215 nanometer according to Woodward-Fieser. So this is the alpha carbon, this is the beta carbon. Okay. Now beta carbon, there is one ring residue. So beta ring residue. Beta ring residue is only 1. So 1 into 12 is equal to 12 nanometer. Now up to here you have this double bond and carbonyl compounds are extending in conjugation with, here it is conjugated, here it is conjugated. So till this point it is extending in conjugation. So higher ring residues will be, one is this, second is this, and third one is this. Okay, so higher ring residues. Higher ring residues. There are 3. So 3 into 5. 15 nanometer. Okay, sorry, 5, not 5. It is 80 for delta, gamma and above. It is 18. So 3 into 80. So it will be 54 nanometer. Now look for double bond extending conjugation. So this one is 1 double bond extending conjugation, second one. So double bond extending conjugation. There are 2. So 2 into 30, the value is 60. Now the second ring is having a homoannular diene component. So only one such ring. So homoannular diene component. So the contribution is 39 nanometer. 39 nanometer. Now look for exocyclic double bonds. How many are there? Exocyclic double bonds. So this double bond is exocyclic to secondary. This double bond is not exocyclic. This is part of the ring. So only one exocyclic double bond. Exocyclic double bond. So you have to add 5 nanometer into it. So on a total you will be getting 385 nanometer for this particular compound. So this is how you will be calculating the lambda max for alpha beta unsaturated carbonyl compounds. I hope you understood the videos very well. Thank you for watching this.